Okay, so yesterday I was a bit confused about something, so I want to just to explain something. Yeah, here I was wondering why we are using C up instead of C. In fact, so remember that C hop is just you have. It's just you reverse like that the tensor product. And the fact here is that we are using this action, this kind of action here, y1, y2 acting on V, which is exactly that. This action, in fact, you need to have C on the left, but C up on the right because it's an action of C up because this is on the right. We reverse the tensor product. That's why you need C up instead of C. So let me write it here. Instead of C. Because right action and A tensor up or B tensor A. Okay. So that's okay. Now, so yesterday we finished by proving. So we mentioned something about the central structure. Yeah, the central structure on this object, this algebra object I1. So we said that the central structure is induced by this. So this central structure is induced by this isomorphism, this collection of isomorphism. And we will use this induced central structure to prove, so the next lemma in the next subsection, but to prove what is important to us is that the center of a fusion category is also a fusion category. So, okay. And it's modular if it is spherical. Okay, so this is in the next section, the duality for fusion category. Okay. Okay, so yeah. So recall. Let me put this way. Recall that. So if you are, you consider a fusion category and module, and what about the dual with respect to the module? This dual is fusion or multi-fusion if you need additional assumption on the module. So recall that a C module category M is exact if and only if it is semi-simple. Moreover, recall that the dual of C with respect to M is a finite multi-tensor category. Multi-tensor category. And it is tensor if and only if the module is indecomposable. Indecomposable. Decomposable. Okay. So the goal of this section here is to show that this dual with respect to M is in fact fusion. Is to show that in this case, so for fusion category, the dual of C with respect to M is also multi-fusion. Multi-fusion. And so fusion if and only if M is indecomposable. Because okay. So we need so what we need to so we just need to show semi-simplicity because a finite tensor category is semi-simple if only if it is fusion. In fact, it's a definition. So it remains to prove the semi-simplicity. Okay. So let me state and prove or sketch the lemma, this lemma, which we will need to prove this semi-simplicity result. And this lemma will need the central structure of I1. So for any wait. Okay. Wait 1 second. Okay. So for any natural isomorphism phi x. So natural transform isomorphism between the identity and double dual. So the canonical isomorphism, so let me, the canonical isomorphism big phi like that. So we will use this phi. So sum over the simple object up to isomorphism. So let me write it like that. Phi x right dual inverse tensor phi x. So this map, so we have that from x to x double dual. So here you map, so this is for this component, and this component will be from right dual to left dual. So sum for x left dual, double dual like that. So you have, so you fix a natural isomorphism between identity and double dual functor you consider this isomorphism depending on this choice, of course, but in fact, the lemmas say that so is this isomorphism is so in the book that did not write that because I guess they identify, but is the image. So let me write it like that. The image by forgetful functor of an isomorphism between I1 and its double dual in the center of C. So in the book that just wrote is an isomorphism between, but we need here we are in the category C, not in its center. You need to consider the forgetful functor, but I guess somewhere in the book that said that they may identify. So maybe anyway. So sketch of the proof. So I don't prove it in details, I just provide sketch of the proof. Consider this isomorphism, but in the Deligne product between C and C up. So sum of X C. So like that. Deligne product from left dual Deligne product to right left dual. So you consider this in so the first step is to show that it commutes with this isomorphism we mentioned before, which is like that. That's home internal home C. So I am just sketching that. We call this isomorphism rho y internal home. Why is it internal? No, it's no more internal home. C. Up. One. Let me check something. Oh, it's okay, I guess. So show it commute in the following sense, I guess, that if, so this is equal to y tensor direct sum of x like that, x. So commute may need that if you apply here identity y tensor this big phi here and here big phi tilde identity y. So you apply this here, this one. So here, this is what we have here. So it's okay. You get something, and here you can also get something, and you want this to commute. So I guess this is, in that sense, that should commute. And the second step is to deduce deduce that the image, deduce that this is the image of a forgetful function of an isomorphism between I1 and its double dual via the forgetful functor. So the second step is to deduce the result using central structure. Okay, because remember that this the central structure on I1 was induced by this isomorphism. The proof is going this way, but I don't want to go into more details. Because it is essentially referring to previous results, and so it's not so convenient to teach. Okay, so here is a theorem that I will provide, for which I will provide details. So the theorem we are interested in, the center of a fusion category is fusion. The center of a fusion category is fusion. So proof. So consider a fusion category. So let C be a fusion category. So as I said, we already know that its center is a finite tensor category. Center is a finite tensor category. So it was stated in the book Theorem 7.16.1, and we covered that, if I'm not mistaken. So it remains to show it is semi-simple. It remains to show semi-simplicity. So as usual, let I, so as usual, the induction functor, so the right adjoint of the forgetful functor is the right adjoint of the forgetful functor. F from the center to the category. So we need first to prove the following claim. So I1 is a projective object, a projective object in the center. So first point. So the ohms. So by definition of right adjoint, you have that. These two functors are equivalent, like isomorphic. So this is right. This is a natural adjunction isomorphism So I is right adjoint. Then, so that's okay. Second point. So the forgetful functor if is exact, so that is known also. Third point. So C is a fusion category, so it's semi-simple. So the unit is injective. In fact, semi-simple, remember that semi-simple is equivalent to every object are projective and injective. And it's equivalent to 1 to be projective and injective. So 1 is injective. Then, if you apply 1 plus 2 plus 3, you get that the functor like that is exact because you have that. 1 is injective, so this is exact, so this is exact. And the funct f is exact. So yeah, 1 is injective and f is exact, so this is an exact functor, so this is an exact functor. So we deduce that I1 is injective. So I1 is injective. Okay. Now recall that for a multi-tensor category, multi-tensor category is called a quasi-Frobenius. Quasi-Frobenius. So, not recall. A multi-tensor category is quasi-Frobenius, and quasi-Frobenius mean, which mean that injective is equivalent to projective for object in the category. This is definition of quasi-Frobenius. So multi-tensor category is quasi-Frobenius. So let me check. Is it proposition 613, remark 614, 613, 614. 6. Yeah, it's okay. Next, so you deduce. So I1 is injective, but multi-tensor category is quasi-Frobenius, so I1 is projective. So we prove the claim. I1 is projective. Now we want to consider the trace of big phi isomorphism. So consider the left trace of so the previous lemma state that the forgetful functor of the big phi is an isomorphism between I1 and its double dual. Previous lemma. Okay, So I guess that trace of the forgetful functor. So let me write it with another color. So trace of forgetful functor of big phi equal, and the book just write it like that. Trace of big phi equal. And so you consider the big phi which is here. So you consider the trace by component like that. So you get direct sum of x in the simple trace of right adjoint of phi x. So right. Inverse trace of phi x, which is equal by definition of formal square norm. So remember, this is what we call by definition of. So I write formal even if it is not written formal because it's not a priori a number. It's just what was called the square norm. That was called the square norm, even if it is not a number in general. So, definition 7.21.2. Okay. Equal. It's equal to. But if I'm not mistaken, we set 7.21.2. There is a result about total positivity. Wait, 7.21.2. Yeah. So if you are in a fusion category, yes, by proposition 7.21.14, this is totally positive, which means that it is positive for any embedding of the algebraic field in C. Something like that. A real algebraic number is totally positive if all its Galois conjugates are positive. Okay, so anyway. So this is equal, so this is the definition of what we call the categorical dimension. Definition of categorical dimension. Let me write we call that is totally positive, which means it's proposition 14. And this C definition, what I said, 7.21.30. Okay. Now, let me continue the proof. So now, totally positive. Now, So wait 1 second. Okay, so now we know that the dimension. So we know that the dimension, the categorical dimension of a fusion category is non-zero for fusion category over the complex field. Of course, it can be zero on the finite field. So this is the book theorem 7.21.12. Okay, so the trace of phi is non-zero. In particular, this trace is non-zero. So you have an isomorphism between I1 and its double dual with a non-zero trace. And the exercise to finish the proof is to deduce that the unit object 1 in the center is a direct summand of the projective object I1 tensor I1 star. Okay, so we need to use this non-zero and to deduce that I1 is a component of this object, which is projective. And so as a component of a projective object, it will be projective itself. So 1 is projective, which is equivalent to it to be semi-simple, the center to be semi-simple. In general, this is a corollary. The semi-simplicity is equivalent to have the unit object to be projective in general. So this is the proof is almost complete. We just need to do this exercise. Okay, so now so next corollary. Okay, so next it's about what did we state at the beginning of this section? The goal is to prove that the dual with respect to is fusion. So we proved the center is fusion. Now we will use that to prove that the dual with respect to an indecomposable module is fusion also. Corollary. So wait a minute. Okay. Let C be a fusion category, and let M be a semi-simple, so exact, C module category. Then, the dual of C with respect to M is multifusion, and fusion if and only if M is indecomposable. So proof. So we just need to consider the indecomposable case, just to prove that this fusion when. So you deduce the semi-simple case from the indecomposable case. So, and it remains to prove that the dual with respect to M is semi-simple. Because we already know it's a finite fusion in finite tensor category. So sorry, I'm not writing very well. It remains to prove. Okay. So how to do that? In fact, we will use the previous result with the center. So by the previous theorem, we know that the center of C is fusion. But C and its dual with respect to M are Morita equivalent, so are the same center. We already mentioned that. So the center of the dual of C with respect to M is fusion to, because it is isomorphic to a fusion category. Now, you consider the forgetful functor from this to this. The forgetful functor F from the center of the dual with respect to M to the dual with respect to M. So it's a surjective functor, always in the weak sense. So it maps projective to projective object. This is the theorem 6.1.16 in the book. So the forgetful functor is a tensor functor. So f of 1 is equal to the 1 of, but this is projective. We know by previous claim that this is projective. Projective by previous claim. So, what is projective? Wait, what? No, wait. No, not like that. we know that one is projective, but one in the center is projective as this is fusion, so semi-simple. So let me write it like that. So that should be next. Here. And this. Yeah. And f is a tensor functor, so in map 1 to 1, map unit to unit. So it's projective. And so it's semi-simple. So the dual with respect to m is semi-simple because we know that semi-simple is equivalent to unit projective. So is semi-simple. It's a semi-simple finite tensor category. So it is a fusion category, which is what we wanted to prove. Okay. 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 So now what about the dimension of the center? So we know we already prove a result about the Frobenius current dimension of the center, that for a finite tensor category C, then the Frobenius parent dimension of the center of C is equal to the square of the Frobenius parent dimension of C, which was stated in theorem 766 in the book. And we will prove this result for the categorical dimension. So for a general fusion category, the same hold for the categorical dimension. And we will state and prove that after the pause. Okay. So let me state this identity for general fusion category. Proposition. So in any fusion category C, we have dimension, categorical dimension of the center equal the square of its categorical dimension. Okay. So the proof, I will have 2 times in the proof, 2 steps. First step, we will assume the category to be pivotal. And next, we will not assume that, but then we will use the construction we mentioned before called the pivotalization, which will be an equivalentization, in fact, C2 equivalentization of the category. And then we will use some result we get with equivalentization and dimension. So let us first prove first when it is pivotal. Pivotal. Let us first when it is pivotal. Okay. So we already know that the center is also pivotal. We already know that then the center of C is pivotal too. It's also pivotal. It was stated in the exercise 7.13.6 in the book. Okay. Now, so let D be the dimension from the pivotal structure of C. With a dimension from the pivotal structure on the category C. Recall again that the forgetful functor preserves the dimension as a tensor functor, I guess. Recall that the forgetful functor F from the center to C preserve the dimension. As a tensor functor. Oh. Okay. As a tensor functor. Okay. Then we preserve the dimension. So we'll consider an element of the Grothendieck ring, of the Grothendieck algebra, in fact. So let us consider the following element in the Grothendieck algebra. So what is Grothendieck algebra? In fact, it's just you make, so in the complex field you say the complexified, but here I have no name for that. You are doing this procedure. So this is a Grothendieck ring, and here it's maybe you can call that maybe the Grothendieck algebra if you like. So consider this an element here, the following element. So the sum for this simple object of the center dz. So it's an element of the Grothendieck algebra. So in the book they mention it as a virtual object of the category, but I don't know what exactly they mean. It's an element of the Grothendieck algebra. And apply. So the forgetful functor induce a map at the Grothendieck algebra level as a tensor functor. So you can apply and use a map we will call F also. F. Yeah. So we use the same name for the forgetful functor here and the map for the Grothendieck at the Grothendieck level. Abuse of notation. Be careful, it is not the same. So sum d z in the center, simple object of the center. So it is a tensor functor. So it is induced by a tensor functor on the Grothendieck algebra. So everything is okay. You can you can commute the f with the sum, and what you get is the following. So you have the sum over the simple, and then you decompose. So you decompose z, so you get something like that. Fz x. So remember that this is the dimension. This is the dimension of the home space Fz1. Fzx. Okay. Now we will do that, and we will use the adjoint of f. So this is equal, by definition, of I Fzx fit to C, the center of Z, Ix. So this is equal to, so we are using two things here. You replace that by that, like that, because everything is finite here, there is no problem. And here you will replace that by that. So it's equal to the sum over the simple in C, sum over the simple in the center, dz, and now you have the multiplicity of z in Ix. Okay, but this is, in fact, this is exactly, so this part, which part? This part is exactly the dimension of Ix. So it is the sum dimension of Ix x, because the dimension is additive, which is, so now let me, which is equal to something And for that, we will need to state a lemma. So some intermediate lemma. Let me write it this color, maybe. Lemma. Dimension of Ix equal the categorical dimension of C, dimension of X. And proof intermediate lemma. Or claim, maybe claim is good. Claim. So we will use this claim for the next equality. So let me state the claim first. Let me prove it now. Because by the previous proposition, by some previous proposition we saw it today or yesterday, I don't remember, yesterday. So this composition is isomorphic to like that. So where is it? X. So is a simple object of C. The tensor X, tensor Z star. Okay. So F is a tensor functor. So if you apply the dimension, you apply dimension plus F tensor functor. So you keep the dimension. You get dimension of Ix equal dx sum dz bar conjugate, which is equal to dx dimension of C. Dimension of Z star is dimension of Z complex conjugate. So I hope this is true in this generality. So D is not the dimension from a spherical structure, so we don't know whether dimension Z equal dimension of Z star, but in general, at least for pivotal, dimension Z star equal dimension Z complex conjugate. I hope I'm not mistaken. So you have what we wanted to prove. So we will use this claim here to get that it is just, so dimension Ix is dimension Z, dimension of C, dimension of X. So you directly get that this is dimension of C sum over X in of dimension X, X. Okay. So let me write it like that. Okay, now so what we get, so we get this equal to this. So let me rewrite it. So get the Fourier functor of the sum of Z in So it's in Grothendieck. It is in the Grothendieck algebra. So it's there is some abuse of notation here because Z should be in the. I should write class of Z maybe. So I should replace. I should write like that because it is in Grothendieck algebra. Let me identify that with that. It's okay. So you have sum. So we prove it is sum for x in simply of C of dxx. Now apply apply the conjugate of the dimension, which is another dimension, which is also a character. Also a character. Or another dimension, it's also a character of the Grothendieck ring. So in the book, they apply D again. I'm not sure it's correct because dimension here is not necessarily a real number. So we should apply the conjugate, but anyway, so what you get is the sum of dimension Z square, which is equal to dimension C sum over x over Z dimension. So this is equal to dimension of the center, and this is equal to dimension of C square. So it's okay. So okay in the pivotal case. So let me just write that. In the book, that just apply D. They apply D instead of D instead of D bar. Why? Because it's not spherical. It's not spherical. If it is spherical, you can apply D because the dimension is real, dz equal dz star. But here, you may need to apply the conjugate. Okay. Now, so if C is an arbitrary fusion category, so without assuming RB pivotal, arbitrary fusion category, without assuming pivotal, so let C tilde be its pivotalization. Pivotalization. As defined before, C definition 721.9. Then the dimension of the pivotalization is just the double of the dimension of C. And C, the remark 721.11 and C is a C2, so C equivariantization, so C2 is a cyclic group of order 2. So, as we mentioned recently, yesterday, in this case, the dimension of an equivariantization is, remember, the square of the order of the group, dimension. The dimension of the center of an equivariantization is square the dimension of the group, dimension of the center. So as mentioned recently, C corollary 8.23.30. Okay. So that's okay. So we are almost done. So the dimension of the center is 1/4 the dimension of the center of the pivotalization, which is, we know the pivotalization is pivotal. So we can apply the previous case here. We get it is the dimension of the pivotalization square, which is, we know that the dimension of the pivotalization is the double. So it is square, so you multiply by 4. And so this simplify with this 1/4. So you directly get dimension of C square, which is what we wanted to prove. Okay. Okay. By pivotal case. Okay. So, where are we? Here. So corollary about this corollary is very important. So let me recall. Before stating the corollary, let me recall the Kaplansky 6 conjecture. I already mentioned that before. So let me recall Kaplansky 6 conjecture for fusion category. So conjecture. Let C be a fusion category. Let X be a simple object. Then the dimension, the categorical dimension of C divided by the dimension of X is an algebraic integer. So this conjecture is open, it's a conjecture, but it's famous. is well known, is famous. It is proved in the following case. It is proved for the premodular case. In the modular case, it is proved in the premodular case. Premodular case. So recall that in the modular case, we have a stronger result. Dimension C dimension divided by dimension x squared algebraic integer. For premodular case, we cannot have the square, but we still so dimension C divided by dimension x is still an algebraic integer. So this conjecture is proved in the premodular case. So let me state it corollary. Let C be a premodular category. Premodular category. So I am still confused in the book that the right bond for it's the same. So is there a difference between right bond and premodular? Right bond 216. So a right bond tensor category is a braided rigid monoid category equipped with a right bond structure. No, I should go to premodular. Premodular category. The premodular category is a right bond fusion category. Okay. So right bond fusion category, as it is written in the book, is a premodular fusion. So premodular, in fact, is assumed to be fusion category. So it's a right bond fusion category. And it is also a spherical braided fusion category. A spherical braided fusion category. So premodular or right bond fusion or spherical braided fusion. They are all the same. So the Kaplan-Cis conjecture is proved for in the braided fusion category spherical. So for each simple object x in the number, so as I wrote before, dimension C divided by dimension x is an algebraic integer. Okay. So that's nice. That's really nice. Okay. So proof. So by the previous proposition, we know something about the center. By the previous proposition, the dimension, the categorical dimension of the center is the square of the categorical dimension of C. Now, because C is spherical fusion, then the center is modular. We already stated that. Moreover, C is braided. So you see the more convenient way to state the corollary is, let's see the spherical braided fusion category, because this is exactly what we use. We use spherical, we use braided. So when you write right bond, when you write premodular, it's confusing. It's not as nice as just writing spherical braided, which is good for me. So moreover, C is braided, so it embeds into its center. There is as a tensor functor. And so for all simple objects in C, we have that it embeds. So in particular, you find the simple object of that. You can find it here. So you can state this result true for modular category. So is an algebraic integer. Result for modular category. We stated last time or 2 times ago. But result for modular category. Remember, we proved that not last time, but using the S matrix. And now we know that the dimension of the center of C is the square, as we just proved by the previous proposition. So the dimension of C divided by dimension of X is an algebraic integer. So we should say, so this is an algebraic integer. Oh, wait, yeah, it's okay. So this is an algebraic integer, which implies that this is an algebraic integer because, of course, the algebraic integers are stable by square root. Which is not true for cyclotomic integer. Cyclotomic field is not invariant by square root. Not every cyclotomic integer is a square, but every algebraic anyway, in the algebraic field, every element is a square, but in the cyclotomic field, not every element is a square. So you have to be careful when you deal with cyclotomic integer. Okay, so this is what we wanted to prove. Okay, so we recover. So in fact, this result is really fundamental In fact, it recovers a very famous result from finite group theory. So this corollary recover a very famous result in finite group theory due to Frobenius. That's why we call that Frobenius type. Called Frobenius type, or one Frobenius. So a fusion category satisfying this property is called a Frobenius type or one Frobenius. And in fact, because we have one half here, this is called modular category. It's called half Frobenius. Okay, anyway. Let me write it. Half Frobenius property. For all x in for all x. Okay. Well, it's simple. For all simple x. Okay, so we recover a very famous result in finite group theory due to Frobenius. So the rep G is one Frobenius, which means that corollary when you are over the complex field. Otherwise, it's not true. So let G be a finite group. Let V be an irreducible representation of G, then the dimension over the field. So the field should be the complex field, or if in general, an algebraic closed of characteristic 0. So the dimension of an irreducible representation divide the dimension, so the dimension of rep G, so that divides the order of the group. Yeah. Proof. The proof is just the previous corollary applied to C equal rep G, which is premodular, spherical braided, and dimension. In fact, pseudo-unitary, premodular pseudo-unitary. Pseudo-unitary. Dimension of C equal Frobenius Perron dimension. C equals the order of the group. Okay. Okay. Here, the field is algebraically closed of characteristic 0. Otherwise, it's not true. Okay. So let me finish by, in fact, the generalization of this corollary to any fusion category. So we cannot state it for any fusion category, for any spherical fusion category, but we can state something which is quite nice. So let me write it as a remark. So let C be a spherical fusion category. Then, so you have, this is modular fusion. Okay. Dimension, that's okay. We already say that before. For all simple objects in the center, we have that. An algebraic integer. So we have this very nice arithmetic property for all simple objects in the center of C, spherical fusion. The dimension of C divided by the dimension of this object is an algebraic integer, which is quite nice. So C is not assumed to be braided here, it's general. In other words, dimension of simple object in the center of C, divide in an algebraic sense, algebraic integer sense, the dimension of C. And that's nice. Algebraic integer sense. That's quite nice. And in fact, so next time, next time, we will apply that to get a generalization of the conjugacy class equation. So from finite group theory to fusion category. So that's really nice. And so it's finished for today. It's end of session.